Offshore oil rigs are among the most massive and complex industrial structures ever built by mankind, standing as floating metal cities out in the middle of the treacherous open ocean. A single modern oil platform is capable of extracting and processing over 170,000 barrels of crude oil every single day, which is enough raw fuel to power entire major cities continuously. Yet, most people have absolutely no idea about the mind-blowing engineering that happens beneath the surface to make this possible. To reach these hidden oil reserves, engineers must drill through miles of ocean water and then pierce deep into the Earth's crust under crushing pressures that would instantly snap normal machinery. They are fighting against some of the most dangerous, unpredictable, and violent environments on our planet, all while operating non-stop, 24 hours a day. The real mystery isn't just how big these structures are, but how they manage to drill straight into the seafloor without leaking a single drop into the ocean, and how they survive massive hurricanes and giant rogue waves without capsizing. If you want to unlock the absolute truth behind how these deep-sea giants operate and discover the secrets buried 10,000 meters below, make sure to like this video and subscribe to the channel right now so you never miss our deep dive engineering breakdowns. To truly understand how this incredible technology works, we have to look back at how offshore drilling first began and how it evolved from simple wooden structures into floating sci-fi cities. Over a century ago, oil companies started by building basic wooden and metal piers very close to the coastline to drill in incredibly shallow waters. As the demand for energy skyrocketed and shallow reserves began to dry up, engineers were forced to push further out into the deep, unforgiving open sea. This led to the creation of fixed platforms, which are massive steel grid structures known in the industry as steel jackets. These jackets were so incredibly large that they had to be built entirely on dry land first. The most famous example of this is the Bullwinkle platform, built by Shell in 1988 for the Gulf of Mexico, which stood at a staggering 450 meters tall and weighed over 50,000 tons. Giant tugboats had to slowly tow this metal mountain out into the ocean, where engineers carefully tilted and sank the entire structure until it sat vertically on the seafloor. Massive steel piles were then hammered deep into the ocean bed to secure it completely, making it literally an underwater skyscraper. While fixed platforms worked perfectly for shallow and medium depths, they became completely impossible and too expensive to build once oil reserves were discovered in ultra-deep waters. When the ocean floor is thousands of feet down, you cannot build a solid steel tower to reach it, so the entire industry had to completely reinvent drilling technology. This gave birth to modern floating platforms, which do not rest on the seafloor at all, but instead function as massive, ultra-stable industrial vessels that float on top of the moving ocean waves. The construction of these floating giants begins in highly specialized, massive shipyards where engineers build them in two entirely separate sections. The bottom section is the base or hull, which often consists of giant hollow columns or semi-submersible structures that can be filled with ballast water to control how the rig floats and maintains its balance in rough seas. At the exact same time, in another part of the shipyard, workers construct the upper section known as the topside. The topside is where the real magic happens, as it holds the drilling towers, processing modules, crew living quarters, massive power generators, and miles of complex industrial piping. The integration of the topside and the floating base is considered one of the most dangerous and impressive heavy lifting operations in human history. In some shipyard designs, the two massive sections are joined together near the coast before being towed out, but in many advanced projects, the heavy base and the thousands of tons topside are towed out to sea completely separate. Once they arrive at the deep-sea destination, massive heavy-lift crane vessels or specialized hydraulic systems slowly and precisely hoist the topside into the air and lower it onto the floating base with millimeter precision. Once connected, the rig must be locked into place over the drilling site so that it does not drift away even an inch. To achieve this, giant steel mooring lines, ultra-heavy metal chains, and highly specialized tension tendons are connected from the floating rig all the way down to massive anchors buried deep in the seabed. On top of these mechanical chains, modern ultra-deepwater rigs use advanced computer systems coupled with automated underwater thrusters to constantly calculate wind and wave movements, automatically firing propellers to correct the rig's position in real time. This extreme precision is non-negotiable because any sudden shifting of the rig could instantly rupture the drilling pipes operating miles beneath the surface. But before a multi-billion-dollar platform is ever towed out, how do oil companies even know where to look in the vast empty ocean? They rely on advanced seismic exploration vessels that act like a giant, high-tech ultrasound for the Earth's crust. These specialized ships sail across the ocean, towing miles of long cables equipped with highly sensitive underwater microphones called hydrophones. As the ship moves, it uses specialized compressed air guns to fire powerful sound pulses straight down into the ocean floor. These sound waves travel through the water, penetrate the deep layers of rock beneath the seafloor, and then bounce back up at different speeds depending on whether they hit sand, clay, rock, or liquid oil. The hydrophones catch these bouncing echoes, and powerful supercomputers process the data to create highly accurate three-dimensional maps of the subterranean geology. This cutting-edge technology allows geologists to see straight through massive, ancient salt layers buried deep under the seabed, revealing massive hidden reservoirs of crude oil that were completely invisible to humanity just a few decades ago. Once a definitive oil reservoir is mapped out, the most dangerous and technical phase of the operation begins: drilling into the deep ocean floor. Before the drill bit ever touches the ground, automated underwater robotic vehicles known as ROVs are launched from the rig to prepare the seafloor. These high-tech robots install heavy guide bases, valves, and monitoring systems directly onto the marine bed. Up on the rig's deck, the massive derrick drilling tower stands tall, supporting miles of heavy steel drilling pipes that are screwed together one by one to form an incredibly long, continuous drill string that lowers through the water. At the very bottom of this miles-long pipe string is the drill bit, which is a heavy, rotating tool armed with teeth made from tungsten carbide or industrial diamonds. These diamond teeth are designed to easily crush and pulverize solid rock formations under extreme pressures and temperatures as the drill cuts deeper into the earth. As the drill bit cuts deeper and deeper into the rock, engineers face a massive problem. The immense weight of the earth wants to collapse the hole they are making. To prevent this catastrophic collapse, engineers must systematically line the inside of the hole with heavy steel pipes called casings. Once a section of steel casing is lowered into the hole, a highly specialized heavy-duty cement mixture is pumped all the way down the inside of the pipe under immense hydraulic pressure. This liquid cement is forced out of the bottom of the casing and flows upward into the empty gap between the outside of the steel pipe and the raw rock walls of the well. Once this cement hardens completely, it acts as an impenetrable safety barrier that stabilizes the entire well structure and completely seals off different geological layers, preventing any oil, gas, or underground fluids from leaking out into the surrounding rock zones or the open ocean. Before we get into the terrifying details of what happens when these high-pressure wells try to explode, take a quick moment to like this video and subscribe to our channel, because sharing these incredible engineering facts is exactly how we keep creating this high-value content for you. To keep the drill bit working smoothly miles beneath the earth, a highly complex fluid known as drilling mud is constantly pumped down the center of the hollow drill pipes. This synthetic drilling mud serves multiple critical purposes at the exact same time. It lubricates the rotating drill bit, cools it down from the extreme friction heat, and carries all the heavy rock fragments and debris back up to the surface so the hole stays clean. Most importantly, the immense weight of this heavy fluid creates massive downward hydrostatic pressure inside the well, which counterbalances the highly volatile, explosive pressures of the underground oil and gas pockets. If the pressure of the underground oil reservoir suddenly overpowers the weight of the drilling mud, a highly dangerous event known as a kick happens, where high-pressure gas and oil rush violently up the wellbore toward the surface. To prevent a catastrophic disaster like a blowout, engineers install the ultimate line of defense on the seafloor: a massive 5-story tall system of heavy hydraulic valves called the Blowout Preventer, or BOP. If the rig's surface sensors detect a dangerous sudden surge in pressure, the BOP instantly activates, firing massive hydraulic rams that clamp down on the pipes with enough force to crush steel, completely sealing the well shut and saving the rig from a massive explosion. In some of the most advanced ultra-deepwater oil fields in the world, the total drilling depth can easily exceed a staggering 10 kilometers from the ocean's surface down into the subterranean rock. Operating a mechanical drill string at these extreme depths requires absolute mathematical perfection, because even a minor miscalculation can cause the miles-long steel pipe to twist and snap like a piece of spaghetti, destroying a multi-million-dollar well instantly. When the diamond drill bit finally punctures the actual oil reservoir, the extreme natural pressure trapped inside the earth for millions of years is unleashed. In many traditional fields, this immense subterranean pressure is strong enough to naturally push the thick crude oil all the way up the wellbore to the surface on its own. However, in ultra-deepwater fields where the ocean pressure is immense, natural pressure isn't always enough. So engineers must install massive, heavy-duty subsea pumps directly onto the ocean floor to help push the liquid up, or artificially inject high-pressure water and gas into surrounding wells to force the oil toward the main production straw. The crude oil travels from the deep ocean floor up to the floating platform through heavy, flexible pipes called risers. These risers are true engineering marvels because they must remain perfectly sealed while constantly bending and twisting to survive the non-stop motion of ocean currents and massive surface waves. When the raw fluid finally arrives at the topside deck of the platform, it is known as crude oil, but it is far from being usable fuel. The fluid exiting the Earth is actually a highly volatile, messy mixture of raw oil, natural gas, salt water, heavy sand, and corrosive chemical impurities. To clean this mixture, the platform acts as a massive floating chemical processing plant, routing the fluid through giant separator vessels. These specialized separators use a combination of intense pressure drops, high temperatures, and basic gravity to cleanly separate the different fluids. The heavy water and sand sink to the bottom to be safely cleaned and disposed of, while the light natural gas rises to the top to be compressed and sent through subsea pipelines or used to power the rig's massive onboard generators. The pure, clean crude oil is then routed into massive onboard storage tanks, built directly inside the floating hull of the rig, which can hold hundreds of thousands of barrels of oil at any given time. Because these platforms are constantly extracting oil non-stop, these massive storage tanks fill up incredibly fast. To keep production moving smoothly without overflowing, massive transport ships known as shuttle tankers sail out to the deep-sea rig every few days. Highly specialized, heavy-duty floating pipelines are connected from the oil rig to the shuttle tanker, transferring millions of gallons of raw crude oil in a matter of hours. These tankers then transport the massive cargo back to specialized refineries on the mainland, where the crude oil is chemically cracked, heated, and processed to be transformed into the gasoline, diesel, jet fuel, and plastics that run our entire modern world. It is mind-blowing to think that every single drop of fuel we use in our daily lives went through this incredibly dangerous, high-pressure, and mathematically precise journey miles beneath the violent open ocean. If you found this deep dive breakdown incredibly helpful and informative, make sure to hit that like button, subscribe to the channel, and drop a comment below, letting us know what extreme engineering marvel you want to see next.